Have you ever watched a thunderstorm and wondered what really happens during a lightning strike? It's not just light and sound, it's an enormous burst of electric current leaping across the sky. Now, in earlier classes, we talked about electric charges, but we mostly considered them at rest. Here's the twist: when these charges begin to move, they form what we call electric current. Take a torch or a battery operated clock. The reason they work is because charges, specifically electrons, are flowing smoothly through wires, just like water flows in a river. This steady movement of charges is the electric current we'll explore in this chapter. And while lightning is short and dramatic, these daily devices operate with steady currents, the kind we'll focus on today. So, how do we actually define electric current? Imagine a wire, and we are zooming into a small cross-section of it. Over time, some positive charges may move forward and some negative charges may move backward. To calculate net flow, we subtract positive forward minus negative backward. Let's say Q is the net charge flowing through in time t. Then current, denoted by capital I, is I equals Q divided by T. That's the basic formula. But real currents aren't always steady. To define instantaneous current, we use a limit. The current at a specific instant is I of t equals limit as delta t tends to 0 of delta Q over delta t. This gives us the exact value of current at any moment. And remember, if current turns out negative, it simply means the direction is reversed. You've heard the term ampere before. It's the C unit of current, written as capital A. 1 ampere isn't just a number. It's defined through magnetic interactions between two wires, which we'll study later. But for now, think of it like this. Most household gadgets run on 1 to 10 amperes. A lightning bolt can deliver up to 50,000 amperes. And inside your body, nerve signals operate in the range of microamperes. That's a millionth of an ampere. Isn't it amazing that the same concept explains both thunder in the sky and signals in your brain?
Let's go deeper. What actually carries this current in a solid? In metallic conductors, some electrons aren't tightly held by atoms. They're free to move around. Imagine a sea of electrons floating in a metal lattice. When you apply an electric field, these electrons get a push. They drift in one direction, even though they keep colliding with atoms. Law: an electric field exerts force on free electrons, causing them to accelerate and create current. So in solids, it's the negatively charged electrons that do the moving. The positive ions just stay put, forming the rigid structure.
Here's something interesting. What happens if there's no electric field? Electrons still move constantly. That's due to thermal energy. They zip around randomly and collide with atoms, changing direction all the time. But here's the catch. Because their motion is random, the net movement cancels out. No direction means no current. So, without an electric field, electrons keep moving, but they don't go anywhere on average. It's like a room full of people walking in every direction. The overall position of the crowd doesn't change. Only when a field is applied does their motion get coordinated. That's when current is born. Let's take a practical example. Suppose 1.5 coulombs of charge pass through a wire in 0.5 seconds. What's the current? We use the formula I equals Q divided by T. That's 1.5 divided by 0.5, which equals 3 amperes. That means in every second, 3 coulombs of charge are moving past a point in the wire. Now, here's an advanced twist. What if charge is changing continuously? Then we say I of t equals dq by dt, the derivative of charge with respect to time. This becomes important when we deal with circuits involving varying currents, like in capacitors or alternating current systems. All right, let's quickly revise what we've learned about electric current. Electric current is the flow of net charge per unit time across a conductor. It's carried by electrons in solids and flows steadily when an electric field is present. We defined it using the basic formula I equals Q by T, and in dynamic cases, I equals dQ by dt. We explored different magnitudes from massive lightning currents to microscopic biological ones. And we understood that random thermal motion alone doesn't lead to current, we need direction from a field. I hope you now have a clearer picture of what makes electric current flow from natural lightning bolts to circuits in your home. See you in the next session where we explore how current behaves in conductors and meet one of the most famous laws in electricity, Ohm's law.